My name is Kamran Naqvi. I'm part of the Broadcom team based in the UK. And today I'm going to talk about accelerating AI with next generation networking. It's a very long topic. So in summary, what I'm going to talk about is I'm going to talk about what are some of the special needs of AI networks. How can we meet them in an efficient way? And although in my title I'm using the term scalable designs, when I'm going to talk about some of these designs, my focus is going to be more on the enterprise networks. Enterprises who are building AI infrastructure. So I will not be talking about multi-plane, multi-tier topologies. I will be talking about GPU clusters which are more realistic for enterprises as we stand today. Okay, so I will start by talking about what are the various networking fabrics we have in an AI infrastructure. It is slightly different from what we have in our traditional data centers. So I'm going to talk about that. Can I ask a quick question? How many of you were present in my last year's presentation? Okay, about 40%, including me. So I'm going to do a little recap of what I discussed last time because it is relevant to my discussion today. And I've been given a little bit more time by Lukash, so thanks a lot. So I will take a few minutes and I will explain how AI networking has certain requirements, certain unique requirements which are not there in the standard cloud computing. Because the traffic patterns in an AI environment are very different from what you see in a traditional cloud computing environment. So I'll give you an idea about that. Then I'm going to talk about some of these AI topologies and AI designs that I was talking about. So this part of my presentation is basically based on an AI reference architecture document that we've written in Broadcom. I'm one of the authors of the document. There will be a QR code at the end of this presentation, so you will be able to download the document. I'm going to take some of the nuggets from that document and I'm going to explain them here. I'm going to explain it in very, very simple terms. So this document is written with this idea in mind that the people who are reading this document, they do not know a lot about AI infrastructures. So how do you explain it in very simple terms that what type of topologies you need in an AI infrastructure, then what type of design you should be doing, what type of cables you are using, what type of optics you are using, what should be the rack layout. So we will explain all of these things in very simple terms. After that, we will get into some of the features we have in SONiC which are catering for special AI networking requirements. As I said, AI networking is different because the AI traffic patterns are different. Then what do we have? What additional features we have in SONiC which can cater for those requirements? I did point to some of those in my last presentation last year. Today, I'm going to double click on those features. I'm going to explain them how SONiC can do a very good job for AI networking. And at the end, if we have time, I will talk a little bit more about Ethernet for scale-up topologies, scale-up networks. So that's the plan. Let's make a start. AI networking fabrics. There are 4 different types of networking fabrics that you will see in an AI infrastructure. Front-end fabric, very simple. That is like your traditional data center fabric. This is the fabric where your XPU cluster is connecting with the outside world. That is where the requests are coming in. That is where the data is coming in. Let me just make another clarification here. In my presentation, I'm going to use the term XPU and GPU interchangeably. At Broadcom, we like to call it XPU because it's not necessarily a graphic processing unit, but GPU is a popular term, so sometimes I'll call XPU, sometimes I'll call GPU. It's the same thing I'm referring to. We're talking about an accelerator for AI applications. So front-end fabric, as I said, it's your traditional AI, traditional data center fabric. Storage fabric, everybody knows what storage fabric is. Out-of-band management fabric, we know what is out-of-band management network. There is no change in any of those fabrics when we talk about AI infrastructure. But look at what we have here, your back-end fabric. That is where all the uniqueness come into picture. Back-end fabric is where your GPUs or XPUs are talking to each other. And the traffic flows in this XPU to XPU communication is very different from what you see in the traditional networking. Now, within the back-end fabric, there are two types of fabric. There are two types of networks. There is a scale-up network, and there is a scale-out network. Now, what is a scale-up network? Scale-up network is for connecting your XPUs within a system. It could be a DGX type server. So how many XPUs or GPUs do we typically see in an AI server? Typically, you will see 8 GPUs or XPUs in one server. Now, these GPUs need to talk to each other, which means that even within a server, you need to connect these XPUs together. The fabric that you use to connect XPUs within that server is called scale-up fabric, right? Now we have some rack scale solutions as well, rack scale systems. You must have heard about NVL72, for example. I'm not talking about those in today's discussion because in my view, they're not that relevant in enterprise environments. They may be at some places, but to keep it simple, I'm only talking about these 8 GPU servers which are available everywhere from NVIDIA, from Lenovo, from Dell, and so on. All right, so scale-up fabric is used to connect GPUs within a server. What is scale-out fabric? You need to connect GPUs which are in different servers. So the fabric that is used to connect GPUs across different servers, that is called scale-out fabric. That is really a scaled fabric, right? Because these AI infrastructure, these fabrics are really, really large. You have thousands of clusters in one fabric, right? So scale-out fabric is used to connect all of these GPUs which are spread across many servers. In my presentation today, my focus is going to be mainly on scale-out fabric. All right. Now, I'm going to repeat some of the things I said in my presentation from last year. I would argue that AI networking, AI infrastructure is a distributed compute problem. Would you agree with me? Now, what is a distributed compute? Distributed compute is when you have a workload, when you have an application which is large enough that you can't run it on a single CPU, on a single compute CPU or GPU. You need to spread it across multiple. You need to distribute it across multiple compute. So that is why it is a distributed compute problem. Think about AI applications. Think about something like ChatGPT-3 or ChatGPT-4. You have over a trillion parameters in a ChatGPT-4. These algorithms are so big. You cannot run them on a single CPU or a GPU. You need to run it on hundreds, thousands of the GPUs. Now think about it. All of these GPUs, they are essentially supporting one application, right? So these GPUs need to act like a single computer so they can support this application. And that is why we're saying it is a distributed compute problem. Now, in a distributed compute problem, I would argue networking plays a key role. Why? Because the performance of your AI infrastructure depends on how efficient is your networking. So networking becomes a key component in AI infrastructures. Second point I'll make here is that the networking requirements for AI infrastructure is very different from cloud computing. And when you use your traditional networking model in an AI infrastructure, networking becomes a bottleneck. If you remember from last year, I gave you an example of what Meta saw in their environment. that networking was the bottleneck for their recommendation workloads. I'm just trying to understand how many people I'm boring. It's just over 50%. So that is my routine. So it's okay, all going well. Yeah. No problem. Yeah. By this time, generally, I start seeing 50% people are snoring. But I think it's like 20% at the moment. So I'm doing a good job. So I'm very proud of this capability, right? When I speak, people feel very sleepy. It's so much so that, I was telling you last time as well, I have a 6-year-old boy. Sometime when he's not sleeping at home, even my wife says, "Can you do your technical presentation?" Works like a charm. So I can see my charm is working on some people already. I'll continue. Okay. Right. So where was I?
6-year-old son.
I'm listening to myself, so I'm feeling a little bit sleepy as well. You can't blame me, right? Okay. So how AI requirements are different. AI traffic is basic. I'm going to make 3 points here. In case of cloud computing, we have small packets, small flows, but we have thousands of these flows. In case of AI backend fabric, scale-out fabric, we have small number of flows, but these are elephant flows. These are very, very large flows, which mean the communication between two GPUs lasts for a very, very long time. Now, what is the problem when you have small number of flows from a networking point of view? Entropy. You do not have a very good entropy. What it means is that you are not able to load balance your communication, your traffic very well. It is like you have a 4-lane motorway, but you're only using a single lane. What will happen? You will have congestion. That is why I was saying that if you use your traditional networking method, in AI networking will become bottleneck because we are not able to load balance traffic properly. Second problem, these are RDMA flows, which means that RDMA has a very poor retransmission algorithm. You know what type of retransmission we use in RDMA? Go back N, which means that if you drop a single packet, you will be retransmitting a large number of packets, depending upon where you did the benchmarking last time. So that's another problem, right? Retransmission. And the last and probably the most important point here is something called tail latency. These machine learning algorithms work in a cyclic manner. There is a compute phase, there is a communicate phase, and there is a synchronize phase. And then you go to the next cycle, and then the next cycle. But the next iteration does not start until everyone has completed the previous phase. This is what I'm showing on this graph, right? So this orange type GPU has completed its job here. This yellow type GPU has completed its job there, but they are not starting the next cycle. Why? Because this gray GPU or this blue GPU has not completed its job. Once it completes its job, now everybody starts again. What it means is that a single slow flow will slow down everybody. And that is a killer for your job completion time. That is why networking becomes a bottleneck in your AI infrastructure if you're using traditional networking models. So what you need is you need special capabilities in the network. So what is lacking? You need special capabilities in terms of load balancing. You need special capabilities in terms of congestion management, right? I'm going to skip some of these slides because I'll be overrunning the time then. So at a network level, the problems are you will see flow collisions, you will see link failures, you will see incast. And if you want to overcome these problems, so for example, to overcome this flow collision problem, you need to have very good load balancing technique. At Broadcom, we use 2 different techniques to tackle this problem. One option is that you can use a packet spraying mechanism. This is probably the best way of doing load balancing. But this comes with a challenge. When you do packet spraying, some of the packets may arrive out of order on the destination. So now on the destination side, on the receiver side, you need to have the capability to reorder the packet. That is one option. The second technique we use is a load-aware ECMP. That is where you do adaptive routing, you understand what is happening, on the network, and based on that you utilize your links. In-cache problem is resolved by, in-cache is the problem when multiple people are talking to one person, right? All-to-all type collective communication. If everybody is sending traffic to me, no matter how much bandwidth I have, there will be congestion, right? No matter how much buffer I have, there will be congestion. So to resolve it, you need what we suggest is you have a receiver-based credit control mechanism. Although in the UEC, now you can have either source-based or receiver-based credit control mechanism, which means that if I am the receiver, I would say, you send me 20 packet, you send me 10 packet, you send me 30 packet, according to the capacity I have. So we are not going to overload the receiver. These are the two options we have from Broadcom. These are the two optimized architecture we have for AI communication. You can either use switch scheduled fabric, which is based on Jericho 3 AI silicon. We have a booth in the expo hall, and we have a switch there based on Jericho 3 AI, if you want to have a look at that. And the other option is you can use endpoint scheduled fabric, which is based on Tomahawk 5 line of silicon, which is more familiar to most of people sitting here. That is where you can use SONiC as a network operating system. Okay. I've already talked about this, right? There's been a number of benchmarking done. When it comes to job completion time, Ethernet outperforms InfiniBand. I mean, because of the heritage, because of, there was a notion at one point that InfiniBand would be better for AI because of its presence in HPC environments. But the number of benchmarking has been done. It has been proven Ethernet is equivalent or better than InfiniBand when it comes to AI applications. Another data point to remember is this failover recovery. Let's face it, if you have a large enough network, there will be failures. When you see a failure, when you compare the failover time between InfiniBand and Ethernet, Ethernet is at least 30 times faster than InfiniBand in terms of failover, right? And this is the worst case scenario. In case of best case scenario, this is not 53 microseconds, it's 37 microseconds. So we can actually fail over 43 times faster than InfiniBand. And a number of benchmarking has been done over the last couple of years, and that is why people who did these benchmarking, they could see which network is better, and that is why Ethernet is the de facto standard for AI networking, I would say, right? 7 out of the 8 mega scalers use Ethernet for their AI infrastructure networking and not InfiniBand. It tells you something. And it can scale to a very, very large number, right? You can build very, very large network based on Ethernet. These are some of the examples here. I'll skip some of these slides. Now, these are the 10 slides I have on different type of designs. So if you want to build an AI infrastructure in your network, first thing you will need to decide is what type of topology you're going to use, right? Closed topology, everybody understand it. That is one option. It is still used in some of the AI infrastructures where you build your backend fabric. Remember, I'm talking about scale-out fabric, backend fabric, GPU communication, right? Closed topology is used, but the most popular topology, the recommended topology for AI workload is rail-optimized topology for scale-out. What is rail-optimized topology? In case of rail-optimized topology, each XPU from a server is connected to a different switch, different leaf switch. So XPU 1 is connected to leaf 1, XPU 2 is connected to leaf 2, XPU 8 is connected to leaf 8. In this topology, we do not refer to these switches as leaf or Tor, we call them rail. These topologies tend to be symmetric, which means that XPU 1 from server 1 is connected to rail 1, and similarly, XPU 1 on server 2 is connected to rail 1, XPU 1 on server 3 is connected to rail 1, and so on. They are symmetric. Why do we use it in this environment? Because the communication collective libraries, algorithms that we have, they are optimized for these type of topologies. What it means is that when you use this type of topology, all your communication will happen just at the first tier of the network. No data will be sent to the spine layer. What it means is that you can, because you are removing essentially one network hop, you're not only reducing the latency, you are significantly improving the performance of your machine learning algorithm. So that is why we say that if your communication collective library algorithms are they are optimized for rail topologies, if they have a rail-aware architecture, that's the term I was looking for. So if they are rail-aware architecture, based on rail-aware architecture, use this topology because it will give you best performance. Now, how does the traffic flow work here? Say XPU1 on node 1 needs to speak to XPU5 on node n. The way communication works is the traffic is not going directly to your topology, as you can see, to the server. Sorry, not going to the leaf. In this case, XPU1 is utilizing its own internal fabric, scale-up fabric, to send traffic to XPU5 on the same server. And now it will only take a single hop and the traffic will reach its destination. Hope it makes sense. Yeah? Now you can ask me a question. You can say, okay, if this is how this communication is happening, I'll take your question at the end. I'll take 50 minutes, I'll keep for Taras's question. It takes 50 minutes, you know. Just kidding. All right, he pays me extra, so I don't mind that, you know. Okay, so the question comes to mind is, if this is the topology, then if this is how the traffic flow works, why do we need to have the spine layer? Makes sense, right? If all the communication is just happening at the first tier, why do you need spine layer switches? The answer is, you don't need it. So if you are 100% sure that all your algorithms are optimized for this topology, you can just make a single tier topology without spine. It is called rail-only topologies or pure rail topologies. But in reality, most machine learning algorithms that we have, they are not 100% optimized for this type of topology. So that is why it is better to have a spine layer. And the second benefit is that this spine layer also gives you a backup path. So if there is an issue within your scale-up fabric, you can use your closed topology type communication and your communication is intact. Is it making sense so far? Okay. Now, I'm getting into some interesting points. You decided what type of topology you want. Second point you have is, how do I connect my leaf switches, my spine switches, and my servers? You can use copper cables, or you can use optics, fiber optics. Which one is better, right? The recommendation, general recommendation, I think everybody would agree with that. If you can use copper, right? Your DAC cables, they are cheap, they do not take a lot of power, and they are very, very reliable. Optics fail, right? DAC cables are going to be very, very reliable for you. They're going to last for a very, very long time. But the challenge with DAC cable is that it cannot go beyond certain distance, right? The standard IEEE standards for 400 gig dictates you can make DAC cables up to 2 meters. We at Broadcom have some very superior SerDes technology, and because of that SerDes technology, which is shared between a Broadcom switch and Broadcom NIC Thor 2, you can actually extend the DAC cable up to 5 meters. This can give you a lot of benefits, right? So if you're using a Broadcom switch and Broadcom NIC, how long can be the DAC cable? 5 meters, which means that essentially you can remove all the optics from your servers for scale-out fabric. Not only it will save you a ton of money, it will save you a ton of power as well. And it's a lot more reliable. And I'll be showing you that topology in the next slide. So use copper, use DAC whenever you can. Second recommendation, of course, you cannot make your whole cluster with just 5 meter cables. You will need longer cables. So if you have to use optics, our recommendation is use very simple optics. There is something called linear pluggable optics. These are optics, but these are the optics which do not have a specific component called DSP in them. That is why we call them linear pluggable. Now, how can we work with linear pluggable optics? We built that DSP capability, that retimer capability in the Broadcom silicon. So if you are using a Broadcom switch, you do not need that fancy optic. You can use a very simple linear pluggable optic. The capability is already built in the silicon. Linear pluggable optics, not only they are cheaper, not only they take a lot less power, they are a lot more reliable as well. Ask me why. Because, thank you. When I often ask people, if you go to, have you touched a optic on a 400 gig switch? Anybody? Have you? No. You said that once, yeah? That's where you were in hospital for a month, right? I often say, if you go to a data center, do not touch the optic because they are really, really hot. You can actually fry an egg on an optic, right? Taras has tried it already. So these optics are very, very hot. But the good thing about the linear pluggable optics is that because they take less power, they run at a lower temperature. And anything electrically, when it runs at a lower temperature, mean time between failure is higher. So these optics are a lot more reliable as well. That's another benefit. And finally, co-packaged optics. This is very wonderful technology based on silicon photonics. We announced it a couple of years back. We've been shipping it for a couple of years. There is a switch at Broadcom booth based on CPO. So if you have time, I would suggest go and have a look at it. You have all the optics built within the silicon. Switch really, really look clean. There is no pluggable optic at all on the switch. So have a look at that, you will like it. All right. Let's give you three or four examples of these clusters. So if you are building a 512 XPU cluster in closed topology, our recommendation is you use a Tomahawk 5 based leaf and spine switch. Tomahawk 5 is 51.2 terabit silicon, which means it gives you 64 800 gig ports. Now, we don't use 800 gig NICs as we stand at this point, which means that you can break out this switch into 128 port of 400 gig. That is how most people use it today. Now, how do you use a leaf switch? You use half the ports for downlinks and half the ports for uplinks, right? Which means that on this switch, on this leaf switch, you can have 64 ports of 400 gig. Everybody agrees with me? Simple enough, right? So the way we design it is we put one top of the rack Tomahawk 5 switch. It can have 64 downlinks. Now, typically in an AI rack, we put 4 servers. Not because we do not have space, but because we do not have enough power. There is a lot of space in these racks. If you go and look at an AI data center, you will see rack have lots of space. So when I was talking about DAC, one of the questions which people ask is, DAC are really thick. They need a lot of space, right? It's difficult to manage them. Not in an AI environment. Your racks have lots of space. You can use the thick cables, no problem there. So typically, you have 8 ports on each server, which means that you have 32 ports in one rack. And because we have 64 ports available, one top of the rack switch can cover 2 racks. We have 5-meter cable, no problem at all. Everything based on DAC. So this type of network you can make 512 XPU cluster, you will need 8 leaf switches, and you will need 4 spine switches. 12 switches in total. If you are building 1,000 GPU cluster, XPU cluster, just double the number of switches, and that's your network. Now look at this topology. It's easy to make it this way in closed fashion. What about rail optimized? Can you use this topology, this type of setup, this type of rack layout for rail optimized? Because remember, with rail optimized, what we are saying is each server is connecting to 8 leaf switches. If we are using the same rack layout, it means stretching a cable from rack 1 to rack 15. That's where your 8 switches. You cannot use a 5-meter DAC there, can you? So that is why, does it make sense, right? So that is why we say if you have that type of topology, that type of requirement, use a middle of row design. In the middle of row design, what you're doing essentially here is you have your networking rack and you are putting it in the middle of your server racks. You can have 4 compute racks on one side, 4 compute rack on the other side. With your 5-meter DAC, you can connect all these servers. It will be a little bit challenging, but you can do it, right? We have customers who have done it. And with this architecture, we recommend you use Tomahawk 5 half bandwidth switch, 25.6 terabit switch, because that's how you can populate all the ports. If you use the full Tomahawk 5 switch, you'll be wasting half of the ports here. All right, enough time there. A lot more detail about all of this is available in the document, which you can download and read. I'm giving 2 options here. One option is for rail optimized design. Option 1 was what you were looking at. With this option, you can scale up to 4096 XPUs because the radix is small. The leaf switch you are using is 25.6 terabit. But if you use, if you can use option 2, that can scale up to 8000 GPU cluster. In this option, basically, you have a end of row design rather than middle of row, where your leaf and spine are next to each other at the end of the row. In this case, your connection between your leaf switches and your server, this is fiber optics. This is linear pluggable optics. But because your leaf and spine are next to each other, now you can connect leaf and spine using DAC. So essentially, you are using same number of optics and DAC cable in this option as well. This option gives you up to 8000 GPU cluster. Okay, I'll skip some of these slides. Now, what are the enhancements we have done in SONiC for AI? We talked about adaptive, we talked about the challenge with the load balancing. In SONiC, we added something called adaptive routing. And we added something called advanced hashing. I'm going to first talk about advanced hashing. I've got 2 minutes, 20 seconds. Okay. Now, in the traditional data center, we use ECMP, and it works fine for us. We use 5 tuples for the hashing, and we can get enough entropy with the source address, destination IP, port numbers. This is enough for us for traditional data center traffic. But with AI communication, as I mentioned earlier, we do not get enough entropy just looking at the 5 tuples. This will give you an idea. So here what I'm showing is that G1 is talking to G3. If you just look at the IP and UDP header, you will see 2 flows. One flow for G1 to G3, the other flow from G4 to, what is that one? G4 to G8. So you will see just 2 links will be used, and you will see congestion. Although there are 6 lanes available, how many lanes we are using? 2. Why we are using 2 lanes? Because at this point, we only see 2 flows, right? G1 is talking to G3, G4 is talking to G8, and that's all we see, because we are only looking at IP and UDP header. But where is the entropy? Answer is entropy is in a header which is behind UDP, which is BTH header. This is where the entropy is, in your base transport header. That is where you have queue pairs. So what you need to do is go beyond UDP header, look in the BTH header and look at the queue pairs, and that is where you will get entropy. That's exactly what we do with the enterprise SONiC. We use something called UDF hashing, where we can look at the queue pair as well. We can include queue pair in our hashing calculation, and there we go. Now we have a lot more entropy, and we can do a lot better load balancing. Last point, adaptive routing. So adaptive routing works in 2 ways. You can do packet spraying with adaptive routing, but what is the challenge with packet spraying? Reordering. On the receiver side, you will need to do reordering. Some customers are using it. Some megascalers use it. They have NICs which can do it. Okay, the option I'm showing here is what we call Flowlet spray. The idea is very simple. The idea is when you look at a flow, essentially that flow is composed of multiple flowlets. What is a flowlet? Which is the packet which are coming in one sequence. So look at this. Packet 1 and 2 are just next to each other, but there is a little bit of gap between packet 2 and 3. Did you notice that? What the idea we have is that if packet 1 and 2 are sent over one route, and packet 3, which is a different flowlet because there is a gap between packet 2 and 3, if packet 3, even it takes a different route, they will arrive in order. Why? Because there is a gap. That's the whole idea. So what we need to do is, on the switch, we need to identify flowlets. We need to identify packets where there is enough gap, and then we can spray them across. One flowlet is using one path, the other flowlet is using other path. Idea is simple. Magic is in the execution. It works very well. So that's your adaptive routing with flowlet spray, which takes me to the end, my last slide. I'm over time. So scale-up requirements, AI, Ethernet can meet all of the requirement for scale-up fabric as well. If the life allow me and I'm here next year, I will talk more about it in detail. But Ram did a very good keynote about this. Scale-up Ethernet can be used for scale-out or scale-up fabric. This is the QR code I was talking about. If you can scan it, you will get the slides as well through Lukash. But if you scan it, you will be able to download the document which I was talking about. Thank you very much for your time.